Ai, bom dia, ladies and gentlemen. Obrigado para estar aqui pelo primeiro seminário de DRCC nesse semestre. Deveria ser semana passada, mas esqueci que temos Páscoa. Então, hoje temos a honra e prazer de ter o professor Kenji Fukushima do Japão. Ele fez o doutorado ele fez a graduação e o doutorado na Universidade de Tóquio. Depois ele foi visitante nos Estados Unidos no Brookhaven National Laboratory no MIT. E depois ele foi postdoc em Kyoto.
CEO of Nobel Prize Outreach.
No Instituto Yukawa, depois ele foi no Instituto Yukawa na Universidade de Keio, e agora ele é professor na Universidade de Tóquio, é um dos fundadores do campo que ele vai falar, que é agora muito ativo e também muito controverso. Tenho a dizer, como sempre, vai ter lista de presença para estudantes, eu vou pôr mas nesse semestre vamos fazer de uma maneira um pouco mais eficiente, eu vou pôr um link no chat, vocês podem preencher, como sempre, seria melhor se você faz perguntas depois, levantando a mão, mas se tem uma pergunta urgente, pode interromper. Ok, podemos iniciar. Kenji, you have the floor. Thank you very much for coming again.
Okay, thank you. Thank you very much for introduction. Even though I didn't understand what was spoken, but anyway, I'm very happy to deliver my talk here. And I was asked to give a very pedagogical talk, understandable for graduate students. So the half of my talk is actually about the lecture on the chiral magnetic effect. And then the last half is about my recent work about the inhomogeneous electromagnetic fields. So here is my talk plan. So as I told you, the first part should be the pedagogical overview. And so if you have any question, please don't hesitate to ask me anytime. And so I will start with the original idea. So not assuming any pre-knowledge from you. And then I will go to the formulation. And then I will briefly introduce some experimental efforts from the heavy ion collision. And then I will explain how this idea is related to the particle production problem under the strong electromagnetic fields. And so the particle production is, of course, a very old subject. But interestingly, if you have special background fields of electric field and magnetic field, then the parity is violated externally, and then the chirality production is permitted. And in such a way, the anomaly can be understood. And so in this way, actually, so this kind of idea is closely related to the experimental confirmation of the chiral magnetic effect in the condensed matter physics. So that idea can be briefly explained, and then I will go into some quantum field theoretical computation of the relevant physics quantity. But then there is actually some controversial point that I want to discuss. And then in the end, I will come to the most exciting story, but this is not yet conclusive because this is still ongoing work. And so I'm still very much confused. And so if you have any idea or any suggestion, so your feedback would be really appreciated. Okay, now let me begin with a pedagogical overview. In fact, the idea can be traced back to the actually 80s or 90s, or the very old story. That is, a QCD vacuum is recognized as a very non-trivial sort of a medium accommodating many topological excitations called instantons. And in fact, it is known that if you see the energy of the QCD vacuum as a function of some winding characterization, which is called a Chern number, then you see such kind of a periodic structure, this kind of a periodic structure, and then the instanton is a very special configuration that can connect different topological characterizations. I mean, if the instanton number, winding number is 1, such configuration can tunnel between the Chern number different by 1, like this. Okay, so this tunneling process corresponds to the instanton, and the sphyron is a special configuration that characterizes this energy barrier. And so typically, this some real-time process to go over the potential barrier is characterized by this sphyron energy. Anyway, the point is that in this way, the QCD vacuum is highly topological. And then the question is how to access such non-trivial topological information from the experimental probes. So that is actually a long-standing problem in QCD. Of course, this is very well understood in theory, but of course, you know, the physics is an experimental activity, and so any theory must be tested by experiment. Then many ideas have been proposed in the past, and actually the heavy ion collision is a very useful the situation to think about this kind of a puzzle, the problem, because the heavy ion collision can create extreme matter that is very high temperature and very high energetic, and so the vacuum structure can be actually changed by the high temperature or strong magnetic field. And under such special environment, you can have a chance to see some topological effect experimentally. And for example, a well-known idea is provided by these people, McLellan and Motola and Shapshnikov in 1990. That is actually a QCD sphyron, and the sphyron is a very well-known notion in electromagnetic sector of the standard model, and that idea was actually a bit, translated into the QCD language, and then the real-time topological transition was discussed, and also around the same age. Around the same year, Björgen proposed a very interesting idea, which is called a disoriented chiral condensate. That is actually because the vacuum is very, unstable, and so there is a chance to have some metastable condensate, having there some abnormal quantum number, namely the parity violating condensate might be developed. Of course, that is, the out of equilibrium and metastable, but it could be possible transiently. And then, effectively, the theta angle can be changed. The theta is actually the parameter in QCD here, appearing here, and usually this is 0. That is experimentally measured, and this is consistent with 0. But in heavy ion collision, this theta could be effectively changed. Okay? So that is very important point. And such kind of idea was proposed, but in fact, so this DCC was not confirmed experimentally. Okay, but a new idea came from a new probe, namely the magnetic field. Okay, so for this idea, there is no need to introduce any magnetic field, but some people recognize that the heavy ion collision can produce very strong magnetic field, and because if you see a non-central collision, then the heavy ions are positively charged, and so if they the collide like this, so this is the geometry seen from above, then this system can be seen like some circular electric current, and then producing a very strong magnetic field in the perpendicular direction, right? And then from a very simple estimate, you can actually get the order of magnitude estimate that is actually 10 to 20 Gauss or GD scale. That is even larger than the typical QCD scale, that is lambda QCD. Okay, and so then these people, Kautev and Maclellan and Wawrinka, proposed the very interesting idea, which is now called the chiral magnetic effect. That is, if you have such a very strong magnetic field, then of course the spin direction is completely aligned. And light quarks, U quark and D quark, they are almost massless, which means that the spin direction and momentum direction should be correlated. Okay, and so, for example, if you see the left-handed particle like this, then the spin and momentum must be anti-parallel to each other. Or if you see the right-handed particle, then spin and momentum, they should be in the same direction by definition. And the idea is, if the heavy ion collision experiment induces some topological fluctuation, or some special kind of gauge background having some non-zero winding number, then from the index theorem, the left particle number and right-handed particle number, that difference is induced by the topological winding number. Okay, so for example, if you have some special gauge field, I mean the gluon field, having the same character as instanton. Instanton have, of course, this winding number +1, -1, +2, -2, blah, blah. And then, for example, the right-handed particle is more induced. You see, starting from this situation, if you have such a special background like this region, then after some time, you can expect that this left-handed particle is converted into the right-handed particle, and then the momentum direction is flipped. Okay, the spin direction is fixed by the magnetic field. And then eventually you have the net momentum direction, that is the electric current in this case. And so in this way, the charge asymmetry is expected if you have such a winding, topological winding and chiral fermions. So that was actually, this is actually the formula proposed by these people, Kautev and Maclellan and Wawrinka. So this idea is very, very similar to the disoriented chiral condensate, okay? But up to this point, the chirality charge was treated, you see, this formula involves the number density here, and also the winding number. So this is also the charge. Everything is charge. But such charge is not a very convenient quantity treated in the quantum field theory. And so, in fact, we invented the chiral chemical potential mu5. In fact, the mu5 is a proxy of the chirality. You know, the chirality charge is a charge that appears naturally in the canonical description. But of course, equivalently, you can treat such charge in terms of the chemical potential in the ground canonical ensemble. And if you take the thermodynamic limit, two descriptions must be equivalent. And so, so this mu5 is a much more convenient quantity treated in the quantum field theory. And in fact, interesting interpretation can be given to the, this chiral chemical potential. That is, if you have space-time dependent theta angle, as I told you, this theta could be shaped furiously in the heavy ion collision event, because the vacuum is actually, changed very rapidly. And so effectively, some condensate can induce effective theta angle, space-time dependent theta angle. And then this theta could be eliminated by some fermion basis transformation. That is U1 axial transformation. And then because the basis is transformed in the inhomogeneous way, and then the derivative is picked up. And so this kind of term involving the theta derivative appears from this, axial transformation. And this is nothing but the chiral chemical potential if this mu is 0. You see, specifically, so, the zeroth component is this, and that is coupled to gamma 0, gamma 5, and psi. And if there is no gamma 5, then this psi bar gamma 0 psi is a density. And so this coefficient is usually the chemical potential, but here you have gamma 5, and so this is actually the chemical potential coupled to the chirality charge. And so this theta time derivative is nothing but the chiral chemical potential, and so mu5 is should be understood in this way. Okay. And then so you can do the calculation of the current, for example, in this setup. So for this computation, it is useful to write down the thermodynamic potential. That is, in fact, in this ground canonical ensemble, the thermodynamic potential is given by the standard formula like this. So this is, of course, textbook formula. But what is not trivial here is you should include the 0-point oscillation energy here. Okay, and also the quasi-particle energy takes a very special form. That is this one. Okay, so usually the energy is momentum squared plus p, the mass squared. But this momentum is changed in this very complicated form. But you see, this P3 is longitudinal momentum, and this magnetic field part, this is in fact very well-known replacement of the transverse momentum squared by the quantum, the eigenvalue in a very similar way as the quantum, the harmonic oscillator. Okay, in the presence of the magnetic field, you have the lambda quantization, and then the Hamiltonian is very similar to the harmonic oscillator, and then that eigenvalue is in fact given by this. And so what is not trivial here is mu5 is coupled to the chirality, and that chirality is given by this. This is nothing but helicity, right? The spin and P3 is a sign of the P3, so this is helicity. So but anyway, once this is given, then the energy can be given by this formula, very simple formula. And once the energy is known, then the expectation value of the current can be computed by the derivative of the energy. Okay, the gauge field A3 and the current, they are conjugate to each other. And so if you take this derivative, then this immediately gives you the expectation value of the current. And interestingly, because of the covariant derivative, A3 derivative is nothing but the momentum derivative. Okay, this A3 covariant derivative always appears together with P3 because A3 dependence is always in the covariant derivative, right? And so this derivative actually gives you this momentum derivative. But remember, the thermodynamic potential involves the P3, the momentum integration, which means that after all, you pick up the surface term, only the surface term coming from the ultraviolet limit, minus infinity and plus infinity. But interestingly, this difference cancels, mostly cancel, but there is actually the finite term remaining even after taking the infinite limit of this ultraviolet cutoff. And in fact, that remaining piece is nothing but a mu5. That appears actually from this term. Okay. And in fact, you have to take the sum over the random level and spin. But in fact, because of this, the spin plus minus sum, the lowest random level, only the lowest random level gives a non-zero contribution. And then eventually, you find this very simple formula. Okay. And interestingly, this formula is completely insensitive to any infrared scales like temperature, mass, and so. In fact, there's no contribution from this summer part, but only the 0-point oscillation energy gives you the finite term. And then, so this is quite natural because this effect originates from the anomaly, and the quantum anomaly is insensitive to the infrared scales, right? So everything is quite natural. And so this is a compact formula, the chiral magnetic effect compact formula. And the interpretation is quite simple. That is, if you have a very strong magnetic field externally, then the right-handed particle the spin alignment is fixed, and left-handed particles, the spin alignment is also fixed, but which means that the momentum direction is fixed like this and this. And so if you have a mu5 favoring, for example, the right-handed particle more, then the net momentum is non-zero and giving you some net current, electric current. So the electric current is proportional to the imposed magnetic field, and of course proportional to a mu5, right? But interestingly, this is the exact formula, okay? In fact, it is also known that a very similar relation holds for the actual current and the magnetic field. That is called the chiral separation effect. If the mu5 is replaced with the density. So if you have a finite density system under the strong magnetic field, then you can induce so J5. But this is quite natural because J5 is nothing but a spin, okay? And so the finite spin is induced if magnetic field is imposed onto the finite density system. Okay, this is nothing but the magnetization or spin polarization, okay? And also, this kind of effect can be understood from the more microscopic picture. So that is, so you can solve the Dirac equation under the magnetic field in a cylindrical coordinate, and then you can do the mode decomposition. I mean, for example, the density can be written in such a way, so there are several components, distinct contributions from spin up, spin down, and different lambda levels, and also the L is angular momentum quantum number, and the K is actually the P3. The momentum along the longitudinal direction, and the particle contribution and anti-particle contribution. And in such a way, the current and actual current and the density and the chirality density and everything can be decomposed in such a way using the complete basis of the solutions of the Dirac equation. And then you can easily find that the current and actual charge satisfy such an interesting relation mode by mode. Yeah, for example, if you see the upspin, the current, then that is actually equal to the upspin chirality density. Okay, and so on and so on. And so this, interestingly, this relation holds for all the lambda levels, not only a lowest lambda level, but all the lambda levels and all quantum numbers. And this is very different from the situation in the actual counterparts. I mean, the J5 and rho, the density, such simple relation exists only for the lowest lambda level. And so, okay, I pointed out such similarity between this formula and this formula, but it is known that this is exact. However, this actual counterpart, this is not exact. I mean, if you have the finite temperature or finite mass, particle mass, then this formula is modified. Okay, this J5 formula is modified. So this is sensitive to infrared scales. And that is actually seen from this model decomposed relation, okay? Because this is actually, the universal relation for all the quantum numbers. So there are significant, cancellations. And then the chiral magnetic effect formula actually appears from this exact relation. However, the chiral separation effect is sensitive to all infrared scales. And so if you see only the lowest lambda level, then the structure is very similar. But in fact, the relation is more non-trivial in this case. I mean, sensitive to many scales. Okay, that is a very big difference, okay? Even though they look very similar superficially. Okay, now let me come to some experimental part. I mean,
Kenji,
yes.
I have a question.
Yes, please.
Regarding the previous slide.
Yes.
Page 11, right? So the lowest lambda level is usually an approximation for weak fields.
Yes. Yeah, strong field.
Right? For strong fields.
Yes.
But this relationship you are showing here is valid for any magnetic field. Right?
Right.
So isn't there usually when you want to study any magnetic field effect, the lowest lambda level is a good approximation for strong fields.
Yes, and in fact,
And now,
so this is, yes, please. Now?
Yeah, and now you see here the universal formula, which
Yes.
is valid for any
Yes.
any value of magnetic
Yes.
field.
And so this is very important point. So this is very important point. So, you know, so from here, in fact, as I told you, if you see some contribution from higher random level, then so of course you can see all the contributions from higher random levels. However, all the terms are proportional to S. Okay, and because you take the spin up down sum, those contributions cancel. And so in the chiral magnetic effect, only the lowest random level survives. The lowest random level gives you the exact result for whatever magnetic field. Okay, the strong magnetic field is not needed.
Yeah, it's not needed, right? So, and this is an exact result.
Right.
Okay.
And so, yeah. And such beautiful cancellation is actually the consequence from this solid relation. But such cancellation does not occur for the chiral separation effect because such beautiful relation does not exist for the actual counterpart.
And why is it so special, the lowest random level? It's because of the spin polarization that the lowest random level is spin polarized?
Yes, the lowest random level is special in the sense that the lowest random level has only one polarization.
Right, and probably that's the reason.
Yes, that is actually the reason. Maybe you know that you see the energy level, then only the lowest random level have only one spin state, and other higher random levels have their spin up and down, and degenerate by 2, and so they have the cancellation each other, but only this one survives. So that is a structure.
Yeah, right. Thank you.
Yeah. Okay. Okay, now let me come to some phenomenology that is heavy ion collision. In fact, this is a very old data, but some star data submitted immediately after the proposal of the chiral magnetic effect. And in fact, so this the result attracted a lot of attention, and the people actually jumped into the a bit hasty conclusion that the chiral magnetic effect has been confirmed experimentally. Well, you see, so this is the horizontal axis is centrality, and so if you go to the more left, the more and more left, then this means that the magnetic field is stronger. Okay, so here the stronger B. Okay. And then the fluctuation was measured, the fluctuation along the longitudinal direction. So this direction, that is actually the magnetic field direction, right? And then such a magnetic field direction is nothing but the direction of the current topologically induced by the chiral magnetic effect. And so because of that current, the charge asymmetry is expected, and then such a charge the fluctuation is measured, and in fact, if you see, as the magnetic field increases, then surely the fluctuation increases like this, okay, or this. In fact, the opposite charge means that this is in fact okay. So you can forget about the opposite charge. This has a little bit complicated interpretation, but the same charge is more straightforward to see. And then, so you see the stronger and stronger fluctuation if you increase the magnetic field. So this is consistent with the expectation from the chiral magnetic effect. However, this interpretation was in fact a little bit misleading. What was measured is actually this cosine correlation function. And so this angle is in fact the angle from the reaction plane. So this is a reaction plane, and so here is the angle. And if you see the cosine correlation function, then cosine is written in terms of a cosine, cosine, and sine. And cosine means that, so this is actually the horizontal distance, and the sine is actually, sine measures the vertical distance, right? And so this is essentially transverse fluctuation minus longitudinal fluctuation relatively to the magnetic field direction, okay? And then the people assumed at that time, that there must be some background. But such, the transverse background and the longitudinal background, they could be maybe the same. And then this background could be canceled out. And also, this horizontal transverse fluctuation is known to be small, and so this can be dropped. And so this cosine correlation should be directly interpreted as a longitudinal fluctuation. This A is a longitudinal direction, okay? And so this should be proportional to the A correlation function. But this expectation was actually completely falsified by this analysis. I like this work very much. So this is actually, the idea is extremely simple. That is, the cosine is surely decomposed into cosine, cosine, sine, sine. But if you take the different sign, not plus but minus, then of course this is cosine, cosine plus sine, sine. And so by combining these two correlations, you can actually disentangle cosine, cosine piece and sine, sine piece, right? And in this way, these authors actually found that this cosine correlation, so this is actually the, this cosine plus 1, this is experimentally measured, and that is dominated by cosine, cosine, okay, so this behavior is completely dominated by this cosine, cosine, not the sine, sine. So this one is almost 0, okay? You see, the sine, sine is almost 0, consistent with 0, but cosine, cosine here. And this means that the backgrounds are dominant, okay? This does not falsify the existence of the chiral magnetic effect, but simply this says that you cannot neglect the background, okay? You see this one and this one. And surely this AA correlation could be something finite, but so this background happens to cancel this AA correlation, and so altogether this one is almost 0. And of course, the background here is also significant. Okay, so this is almost 0, but still this one is something finite. And this experimental data is actually dominated by this contribution. Okay, and so it is very important to subtract such background effects. And there are many ideas so how to subtract the flow background effect. But so this is actually a very hot topics, but this is a little bit complicated story. So if you are interested, of course, I can give you a more detailed explanations, but let me stop here and what? Oh my God, excuse me. So yeah. Yes. Now, let me come to the, my next topics. That is how to understand this phenomenon in terms of the particle production. Okay. Okay. So this kind of physics, the chiral magnetic effect, can be actually understood as a realization of the chiral anomaly. And to understand that, the good situation is actually a 1+1 dimensional system. In 1+1D, everything is transparent. And in fact, in 1+1D, you can find the right-handed particle branch here and left-handed particle branch here. And if you impose the electric field, then the electric field, the particle is actually pushed up from the Dirac sea. So here is a Dirac sea, okay? And then as a result of the electric field, the particle is pushed up from the Dirac sea, and then the right-handed particle is produced. And simultaneously, the left-handed branch, this is actually pushed down, and then the one hole is produced here, which means that you have actually the particle production and also the hole production or antiparticle production. So in this way, in this strict 1+1D system, you have such a particle-antiparticle pair production producing their chirality, net chirality, because this is a right-handed particle and this is left-handed antiparticle having their right-handed chirality. Okay, and so the chirality 2 is produced every time you have such a pair production. So in this way, actually, the chirality charge is no longer a conserved quantity, but this, the production rate can be estimated by the time necessary for this process. That D2 is the incrementation of the chirality, and this delta T is the time necessary for this process that you can estimate from this relation. Okay, and in this way, you can get some anomaly relation in 1+1D. Okay, so this is actually the covariant expression, but this is simply given by E, proportional to E. And if so, this is translated into the covariant expression, then you can write in this way. Okay. And such 1+1D expression can be easily extended to the 3+1 dimensional expression by including the random generality factor. That is, this is 1+1D, but suppose you have very, very strong magnetic field, then the system is reduced into the 1+1D, but the transverse degrees of freedom is actually given by this random generality factor. Okay. And so the 3+1D formula can be recovered by putting this factor. And in this way, the chirality generation rate can be given by this E times B. Or again, this formula can be expressed in the covariant way, and this is a result. And this is a very well-known formula of the chiral anomaly in the presence of an electromagnetic background. Okay. And then in this way, so you can now understand that the anomaly can be understood in terms of particle production, right? So that is very clear in this picture, okay? And from that consideration, it is quite easy to understand or to imagine what should happen for the massive theories. So far, my consideration is limited to the massless theory, but that can be easily extended to the massive theory because the particle production formula is already known, and that is called the Schwinger production formula. Okay, the Schwinger formula, and then the mass dependence is given by this exponential. Okay, and so if the mass is much larger than the applied electric field, then you have the exponential suppression. And so this electric field should be bigger than the particle mass to get the pair production. And so this critical strength of the electric field is usually called the Schwinger threshold or Schwinger critical mass, the field, the strength. Okay. And so in this way, anyway, it is very clear how the particle production, pair production, and chirality production are connected, especially when the magnetic field is very strong. Okay. But there is a puzzle here. That is, if you see the chiral anomaly, then the anomaly relation in the presence of particle mass is given by this. Okay. So, up to this point, I neglected the mass effect, and then the anomaly relation was given by simply this. But if you have the mass, then the axial symmetry is explicitly broken. And so the N5, J5 is no longer the would-be natal current, but there is some explicit breaking term, which is given by this. Okay. But this M dependence looks very, very, very different from this M dependence, that is exponential suppression, right? And so some years ago, I was very much puzzled by this seeming difference. And so we try to understand how this formula could be understood from this anomaly relation. And in fact, if you see this expectation value must be non-zero because this is, of course, parity odd quantity. But if you have electric field and magnetic field parallel to each other, the parity is broken, explicitly. And so this condensate must be induced and should be proportional to E and B. Okay. And then, so we actually did explicit computation, and surprisingly, the result is really beautiful. That is, if you do the real-time formalism, if you do the some field theoretical computation in the real-time formulation, the Keldysh formalism, then the in-out expectation value of this expectation value is in fact given by this. This was first obtained by the Schwinger in 60s or many years ago, decades ago. Okay, but surprisingly, if you plug this expression into this relation, anomaly relation, you have 0. Okay, so the chirality production is 0, simply 0. But this is natural because this is in-out expectation value, right? Not the real-time expectation value, but this is amplitude. Or in other words, if you do the, for example, the finite temperature imaginary time formalism, then this is in fact the quantity you compute in Euclidean space-time. And that is actually the computation in equilibrium. And in equilibrium, the particle production is prohibited because, that is equilibrium, right? And so nothing happens. And so this is simply 0. That is quite natural. And more interestingly, if you do this computation, the same quantity, but in expectation value, then you have something additional here. That is, so you have actually some first term that is the same as this one. And so, this first term cancels this term. However, you have exponential term here. And this gives you the formula that is completely consistent with the Schwinger formula. So this is actually a very beautiful computation we did. And so I was really surprised, but this is actually one of my favorite paper. So this is really a nice computation. Okay. And so in this way, actually, you can also understand the chiral magnetic effect without using mu5. That is really nice because mu5 is a bit subtle quantity in the quantum field theory. And so in this way, actually, for example, you can actually think about such a situation like the electric field in this direction and magnetic field with some finite angle between E and B. And in this way, you can actually expect some special current that is perpendicular to the electric field, and that is actually the chiral magnetic effect. And in this way, the chiral magnetic effect is very analogous to the Hall effect, okay? But along the magnetic field direction, okay? The Hall current is perpendicular to both E and B, but CME is along the B direction, okay? And actually, this kind of problem can be solved. And in fact, so many years ago, we explicitly solved this problem. And the idea is very simple. If you have E and B parallel to each other, then you know the Schwinger formula, and then the chirality production at this point can be solved. Okay. And so if you do the Lorentz boost in this direction, the E is tilted like this, and the B is tilted like this, and then making the finite angle between E and B. And also, because the particle production occurs here, because of the presence of E and B, that is accelerated by the electric field. Okay, and so you have actually the current here. Okay, and so that current has actually the finite angle relative to the E and the B, and so having the actually the component perpendicular to the electric field, and that is actually nothing but CME current. So in this way, by performing the Lorentz boost, so you can actually get the exact result using the Schwinger pair production formula. And from this consideration, it is obvious that the current generation rate, the current time derivative is proportional to the particle production rate. right? Because with this rate, you have the particle production here. And that produced particles are accelerated by the electric field. And so this current is proportional to this one. And this is actually, this CME current is some component, some projected component of this produced current. And so the current generation rate is proportional to the chirality generation rate, okay? Or in other words, the CME current is proportional to T. This is actually important point in data discussions. Well, and in fact, in the condensed matter physics setup, it was known that, okay, so this is a little bit too complicated situation. This is already very simplified setup, but very clever people recognize that even simpler situation is good enough to see CME. That is, if you have E and B parallel to each other, and that is very easily achieved in the condensed matter physics experiment. You know, if you have the material here, then that is actually connected to some, you know, some battery, and then the producing some electric current that is always associated with the electric field. And then you can put a magnetic field externally. And then this E dot B gives you some N5, you know, this is, okay, the chirality production rate is proportional to E dot B. And so N5 is produced, and that produced N5 is coupled to the magnetic field producing the current. And so in this way, the CME current must be proportional to the B squared, or in other words, if you measure the electric conductivity, the conductivity must have a component proportional to B squared. That is the idea, okay? And if you confirm such B squared dependent electric conductivity, that must be the signature for the chiral magnetic effect or chiral, you know, the chiral anomaly. That was the idea. And in fact, these are BNL people, these are experiment using a biosem metal. And in fact, you see, this is a magnetic field. The horizontal axis is a magnetic field. And this angle is a relative angle between the electric field and the magnetic field. And this zero means perpendicular to each other. Okay, and 90 means the parallel to each other. This is a little bit confusing, but okay. So if you magnify this result, parallel to each other result, then you see if the temperature is low enough, this is a resistivity. Resistivity decrease as a function of increasing magnetic field, and so this suggests that the conductivity, that is in fact the inverse of the resistivity. This must be a proportional to B squared. Okay, that is suggest, you know, seen from this behavior. If this suppression is like 1 over B squared. Okay, and so now people consider that this is experimental confirmation of the chiral magnetic effect. Okay. But of course, for their full justification, the field theoretical computation of the electric conductivity is indispensable, right? Of course, this is a very, you know, hand-waving argument. And in fact, if you see the original paper, they assumed the relaxation time approximation. But here, there is a very crucial assumption. That is, they assume that the relaxation time does not depend on the magnetic field. Okay, if the relaxation time depends very non-trivial magnetic field dependence, then this conductivity may have arbitrary magnetic field dependence. Okay, and so the microscopic computation is of course indispensable, and so we did that. But for this computation, unfortunately, the lowest random level approximation is not sufficient. That doesn't work, because if you assume that the magnetic field is very, very, very strong, and if the system is assumed to be a 1 plus 1D, then the lowest random level means that you have only the 1 plus 1 dimensional dynamics. And then this kind of, you know, the scattering processes, all the processes are prohibited. Okay. And then there's no scattering. No scattering means that the conductivity just diverges. Just like the shear viscosity. The viscosity diverges if you have just, no interaction, okay? So you must consider actually the higher Landau levels. And so we studied from the Kubo formula, of course. This is the elementary formula to compute the electric conductivity. And then, so this is a little bit technical detail, but some hydro mode must be subtracted. Otherwise, you suffer from some division by 0 because of the 0 mode. The hydro mode is a 0 mode. And so the hydro mode must be projected out for the computation of the transport coefficient. This is actually the generally so. Anyway, now because you have the magnetic field, the conductivity has a tensor structure. And you have to do the tensor decomposition. And this longitudinal component, this longitudinal component, this is in fact the CME relevant component. And of course, also there you have the whole conductivity and some transverse conductivity. But so this is actually very difficult to estimate, okay? And this is actually the piece of cake. And the CME part, this one is actually the most interesting part in our context, okay? And technically speaking, this is actually a little bit complicated, but at the end of the day, what you should solve is a kinetic equation because in the diagram, there are many pinch singularities, and you have to sum all the pinch singularities. And that can be done using some Dyson equation. And then the Dyson equation gives you some kinetic equation like this. Okay, this is very similar to the Chiral kinetic equation, but more, how to say, more like the Dirac equation actually. And then by solving this, in fact, you can actually, this F is actually the distribution function constructed from the fermion basis, the spinor. And then what you should do is taking account of these collision integrals, you have to actually solve the distribution function in the presence of the electric field. Starting from some equilibrated distribution function, such distribution function is a little bit distorted by the effect of applied electric field. And such distortion is, of course, proportional to the electric field, right? Together with some trivial kinetic factor like this, okay? Anyway, if such distortion is computed, then the induced current, electric current, is of course given by such a distorted distribution function that is of course proportional to the electric field. And so from this proportionality relation, the coefficient can be read. And this coefficient is nothing but electric conductivity, right? And in this way, electric conductivity can be computed. And that we did. That is actually, the strategy is quite straightforward. You should solve these kinetic equations by linearizing. Okay, I mean, assuming that delta F is small and linearize the theory, and then you can actually make the solve the delta F. But that is actually that has some schematic structure, like for example, some operator applied to the onto the some delta F, and that is given by some the scattering, the collision integral, and so in principle, if you do this computation, then delta F can be solved. But as I told you, the hydro mode is 0 mode, and so in fact this matrix, this operator involves 0 mode, and that is associated with hydro mode. That must be projected out. Otherwise, you have a 1/0. Okay, and so so we very carefully treated that, and then we solved everything. And so here is a numerical result. That is really nice. And so we did this with Yoshimasa. And you see, as a function of the quark mass, you see the electric conductivity. And as a function of the magnetic field, you see this is resistivity. So you see the resistivity has a decreasing behavior as a function of the magnetic field. And this is consistent with what has been seen in the condensed matter physics experiment, right? So this is very nice, the field theoretical derivation of the negative magnetic resistance, right? But in fact, there is one subtle point. That was actually pointed out by the referee. That one of the referees was extremely, nice. And in fact, we realized that we have overlooked one important thing that was pointed out by one of the referees. Well, in fact, what is the problem is that if we take the massless limit in this region, okay, the massless limit, if you perform the lowest random level approximation, then, as I told you, the conductivity is divergent, okay? But of course, if the quark mass is finite, then the scattering process is also there, possible, and then the conductivity is finite. But still, anyway, some crazy behavior is seen from here. But in our computation, everything is smooth. And so this is a very nice behavior, but still, this region is still very dangerous. Why? The reason is, even with their scatterings, the scattering would not change the chirality, okay? Because this is a quark-gluon fundamental processes. And so, of course, the gluon does not change chirality, right? And so if you take the massless limit of the theory, then even with the scattering processes, the chirality must not be changed, which means that the chirality decay is not involved in this computation. This means that N5 does not decay, okay? If you impose B and E for a long time, then the current is generated, and then the current is eventually should be a proportional to time, T. And this means that, if this is true, then the conductivity is of course divergent, okay? So the true physical result must be actually the infinite conductivity in this setup. But in fact, in our computation, this N5 was not treated as a microscopic quantity because the delta F was assumed to be a very small number, and F was assumed to be just equilibrium quantity, okay? And so this N5 that could grow linearly with increasing time, that was actually not included in this computation. So in some sense, this N5 was projected out by hand. And so this is a sort of a hydro mode, but that hydro mode was, subtracted by hand. So actually, the field theoretically speaking, our computation is still, the meaningful and well-defined. But nevertheless, the physical answer must be divergent. Okay, so in this limit. Well, so this is very subtle, extremely subtle. But anyway, and so some, the caution must be anyway, so this is just a comment. Well, now I think that my time is up, but okay, so let me very briefly and quickly go through my ongoing project. That is a standing wave, okay, idea. Okay, now we actually are thinking about the very special electromagnetic profile to think about the chiral anomaly. Well, usually, the electromagnetic waves have their E and B perpendicular to each other, right? If you have the electric, the field like this propagating like this, and the magnetic field must be polarized. Like maybe this is not really a good, illustration. But anyway, so maybe you know what I mean. But there is a very special type of solution of free Maxwell equations. having actually the E dot B. I mean, the E dot B is non-zero. This is possible only, even for the solution of the free Maxwell equation. This is really surprising, right? But this was discussed in this paper. And in fact, the very general solution was constructed from the Maxwell equations, okay? This is actually a family of solutions. This F is an arbitrary function of Z plus T, and G is arbitrary function of Z minus T, okay? And then you can prove that, okay, and also together with EZ and HZ is 0, okay? So this is a fully transverse, okay? Z is somehow the electromagnetic propagating direction, and E and Y, the X and Y, that is transverse. And so this is a fully transversely polarized electromagnetic field. But anyway, so you see, it is obvious that E dot B is non-zero here, right? But still, this is a solution of the free Maxwell equations. This is extremely interesting, right? And so this is actually the concrete realization of the local parity violation, right? As I told you, in QCD context, the local parity violation is very important to introduce a chiral magnetic effect or heavy ion collision or the disoriented chiral condensate, or, the QCD itself does not break parity. But locally, such violation is allowed. And in the same way, the Maxwell equations accommodate such local violation of parity, right? So this is a very, the beautiful example of a local parity violation in a theory that does not break parity explicitly. Well, and in fact, this is actually a helical standing wave. Okay, the point to have such a special configuration is that this is a standing wave. In some sense, a superposition of oppositely propagating electromagnetic waves. And this is one example of the vector potential. And then you can easily see that E dot B and E squared minus B squared, these are Lorentz invariants, and they are actually time independent, even though the electric field and magnetic field individually have the time dependence, the oscillating fields. But E dot B is given by such a simple expression, okay? So this is extremely interesting situation setup. And then the question is how to saturate the chiral anomaly relation. That is this one, okay? And we are now attacking this problem. And there are several suggestive results. One is one hint comes from the Chern-Simons current. Okay, so using the vector potential that I wrote down here, you can compute the Chern-Simons current. Okay, then the Chern-Simons current is simply given by this in this simple U1 system. And the important point is that the actual current is, of course, not conserved current anymore by the effect of the chiral anomaly, but this combination together with the Chern-Simons current, this is a conserved current, okay? And particularly, this zeroth component is known as a magnetic helicity, and if you do the spatial integration, this is gauge invariant. And so this is actually, this K0 is a physical quantity. And so in some sense, the many people argue that the chiral anomaly is a process of the helicity exchange between the matter sector and the electromagnetic sector. That is namely the magnetic helicity, okay? But here, the magnetic helicity is 0, okay? K0 is 0. But for this standing wave, only the spatial component appears in the Chern-Simons current. This is hint number 1. And there is another hint. That is, we also computed Lipkin-Zilch. Zilch is a very interesting quantity in free Maxwell equation. That is, the free Maxwell equations have infinite numbers of conserved charges. Okay, you can construct arbitrary, some infinite towers of the conserved charges are expressed in this way generally, and that is associated with some continuous transformation or symmetry of the heaviside transformation. But anyway, this simplest one, the 0, 0 component, the simplest one is given by this, okay? And this is called, sometimes called the optical chirality, okay? And this is gauge invariant object. Okay, the Chern-Simons current is of course not gauge invariant, so the physical interpretation is subtle, but this is gauge invariant. And then we found that the Dutch charge is 0 again, but the Dutch current, Dutch component, the spatial component is non-zero, and this is constant. This structure is somehow similar to the Chern-Simons current, right? The charge is 0, but only the spatial component appear. Okay. And so, in fact, so this situation is extremely interesting because usually the anomaly is understood in terms of the particle production, but that interpretation is possible when N5 appears or the zeroth component appears. Okay, zeroth component is the dominant piece, but in this case, the zeroth component is 0. Supposedly 0, okay? And so some spatial current must play an important role. But this system is very difficult to solve. And so we actually considered in a simplified version of the theory, that is some system, similar system in 1+1 dimensions, okay? Then we considered such inhomogeneous electric field in 1+1 dimension. And then, so that everything is solved, can be solved in 1+1 dimensional system for arbitrary background fields. Okay, so this is just one example, but for arbitrary background, you can write down the solution of the Y equation, and then you can compute whatever current. And this is in fact the result if you have such a situation. And in this case, you can also show that this current is actually the same as completely balanced with the Chern-Simons current, even though the Chern-Simons current itself is not gauge invariant. Well, but this is a extremely non-trivial situation, okay? The 1+1 is so simple, but this is still very non-trivial because, this electric field is oscillating field in coordinate, Z. But so this situation does not permit the particle production. Okay, this is very different from the constant electric field. If you have the constant electric field, then as a function of this is a spatial coordinate. Then, if you have the static potential, then the energy is tilted like this, and so the tunneling process is possible. However, if you have such electric field or the vector potential like this, okay, then there is no such tilted structure, but simply the oscillation like this. And so there is no tunneling. And so the particle production is not induced by this type of electric field. And so, this anomaly is saturated not by the particle production, but the spatial component of the current. And interestingly, the spatial component or the J5, the spatial component of this current is in fact the spin. So in this system or with this standing wave system, the anomaly is actually explained in terms of the spin polarization. Okay, not the particle production, but the spin polarization induces the current, the anomalous effect. Okay, so this is extremely interesting because the spatially, the local parity violation may have the anomalous effect that eventually leads to the spatially modulating spin distribution. Okay, I think that this may have some effect on the interpretation of the local, the polarization. Some, the lambda bar polarization can be, measured locally, and probably the local polarization may have such anomaly origin coming from this kind of, mechanism. Well, okay, so this is actually, okay, the last slide of my talk. So, okay, in summary, my conjecture is, this is still conjecture, there is no proof, but my conjecture is that E dot B, the anomaly, have actually two contributions. That is, one is the spatial part. Okay, E dot B, this is the right-hand side of the anomaly relation, and that can be further decomposed into the time derivative part and spatial derivative part. And usually, this part, that is actually given by the magnetic helicity, but with the standing waves or some special profile of a local parity violation, this might be vanishing. And then only the spatial component gives you the anomalous, contribution of E dot B. And then the question is, what should be the physical interpretation of this, spatial component? And interestingly, if you decompose electromagnetic angular momentum, then the electromagnetic angular momentum has a very similar contribution like this. Okay, this, you see, they are the same. And so the anomaly could be provided by the spin or some kind of a helicity carried by the electromagnetic wave or the standing wave. So that is actually the very interesting possibility to probe the chiral anomaly with some special profile of the electromagnetic background. Okay. Okay, now, so this is actually the summary. Well, so the electric conductivity is a very important quantity to confirm the chiral magnetic effect, but the full computation is not yet complete. And so we did some quantum field theoretical treatment, but still the N5 we cheated the treatment of N5. And so such complete treatment is desired. And also we are actually doing some complementary approach using the holographic QCD model, namely the Sakai-Sugimoto model. And we already have result, but my student is holding the result for a long time, like 2 years actually. I always persuade him to publish the results soon, but he's still working on the draft. And so anyway, we already have some results from the holographic QCD model. And also the chiral anomaly with standing wave. This is really interesting because this may open new possibility to see the anomaly effect from the spin. Okay. That may or may not be related to the local polarization problem of lambda and lambda bar seen in the heavy ion collision. And so in such a way, the local parity violation might be directly related to the chiral anomaly through this, the spin helicity exchange. Okay, that is my conjecture, and I'm working on this project, and this is a still ongoing project, and so any feedback from you would be really appreciated. Thank you very much.
Thank you very, very much for the presentation. Any questions? Por favor, levanta a mão, raise your hand, or just speak up.
Yeah, I have a question, Kenji.
Yes, please.
How can you produce a standing wave in a heavy ion collision, say? Because I think these are propagating waves. And how can you
so this is
standing electric fields?
Well, the important point is that this standing wave, or generally this standing wave, this is a solution of the Maxwell equations, okay?
Right.
And in fact, if you consider the initial condition of the heavy ion collision, the initial condition is given by Grasma. That is actually the classical field, the classical solution of the Yang-Mills equation. That is very similar to the Maxwell equations, right?
Yeah.
So essentially, the initial condition of the heavy ion collision, that has a very similar structure as this standing wave solution.
Electromagnetic.
Yes.
Okay. Okay, I have to think about it. Thank you.
Anami, do you have a question? Please speak
Yeah,
up.
I have a question. Thank you for the talk, Kenji. So I was a bit confused about these hydro modes you projected out. So is it a subtraction you did?
Well, it is okay. Precisely speaking, that is not project. It is yeah. So that is not a subtraction, but it is actually projected out. So it is a sort of a projection. So even though well, yes, even though this matrix or operator has a zero mode, but if you appropriately set up the basis, then such zero mode gives you zero, just a zero. Okay, in the left-hand side, you know, that is a zero eigenvalue, and so this is zero, right? And so, if so, you expand this with some proper basis, then such zero mode part is actually projected out, and so that is completely harmless. Okay, that is what we did.
But then you have to do that if you have finite mass, but to explain the situation for zero mass, you cannot do the same procedure.
Yeah, so, okay, so the subtlety I mentioned was that if the mass is zero, the N5 is you know, conserved quantity in this system, and then any conserved quantity constitutes the hydro mode, right? The hydro mode comes from the conserved quantity like you know, energy or particle number, or then the chirality becomes the hydro mode. But such, you know, the possibility of N5 being the hydro mode is actually excluded from the beginning in our treatment. But that is not fully justified. So in such a sense, you know, so this behavior is not fully justified. Okay.
Okay.
So this is a very subtle point.
Okay, you assumed it, and it was convenient for you to assume it for finite mass.
The full treatment of N5 as a hydro mode is a bit difficult. Well, I mean, in our setup, so F is, you know, yeah, this distribution function was decomposed into the equilibrium distribution plus delta F, okay? But to treat N5 as a hydro mode, this must be changed, and this must be also the, you know, further decomposed into the right-handed part and left-handed part separately.
Okay.
To accommodate the, you know, net chirality charge. And so this, you know, the whole formalism must be more generalized.
I see.
I think
okay.
this is a common thing, right? What happens if microscopic and macroscopic things start talking to each other? No one really knows. Yeah. I mean, regarding this, I have a question, and I mean, sort of a general thing that you mentioned disoriented chiral condensates in the beginning. And people said that disoriented chiral condensates have this, no one really knows what their characteristic size is because it depends on things that we can't, if they're too small, it's a pion, right?
Yeah, yeah.
If they're too small, it's a pion. If it's also called a pion. If they're too big, then they're much bigger than the heavy ion interaction. And something similar could happen with domains of, with chiral domains. Do we have an estimate in your chemical potential sort of thing? You kind of assume that they're big, but yeah, do we have an estimate of their characteristic size?
Yes. Yes. So yes, yeah. In fact, that is actually illustrated in this cartoon. And so you know that the initial condition of the heavy ion collision is given by a Grasma, right? So well, yeah. So this is actually this cartoon describes the Grasma initial condition. That is a solution, classical solution of the Yamio's equations. But the typical size of the Grasma, typical energy scale is given by the saturation scale, right? And so all the transverse size scale is also given by this saturation scale. That is 1 GB scale. Okay, and also typically this one fracture, this size is something like 0.2 femtometer or something. Right.
But so this is just dimensional analysis, right? I mean, you don't know if
what do you mean by a dimensional analysis? What
you're doing is, what you're saying it's a bit like, I mean, it's a general thing. It's like the lifetime versus the real versus the imaginary part of any correlator, right? I mean, you don't know whether the the characteristic size of the topological fluctuation and the characteristic lifetime of the topological fluctuation all go as QS rather than as 10 times QS or something like that, right?
Mm-hmm.
In a sense, what you're doing is you're throwing a coin a certain number of times, and you're hoping to catch a fluctuation so that the head and tail give you a difference. That's what you're doing.
Wait. So you are talking about the two different things simultaneously. So okay, I'm now talking about the spatial size. And the spatial size is surely characterized by QS. But you are also talking about the time scale. Okay, the time scale also involves some coupling constant. So, as you say, yes, the QS simply gives you some dimension, but that is, of course, come together with some power of the coupling constant. And so, yes, the time scale is more subtle. Yes.
Any more, just to say that this is actually related to this hydrodynamics problem, right? Because eventually you start to your dynamics and your characteristic size of the topological regions will start talking to each other.
Yeah.
Any more questions?
My guess.
Please go ahead.
Okay, yes. Okay, my picture is that I think that the CME must be the very early time dynamics, even before the hydrodynamic regime. Of course, I know that there are many excellent works on the anomalous hydro, which I like, but the lifetime of the magnetic field is maybe not long enough, right?
Actually, about this, I actually have a sort of follow-up question, that the lattice calculations that have been done on this, Zoltan Fodor had a calculation on this.
Yes.
Show that the topological susceptibility kind of very quickly goes to zero after above TC. Yeah, I don't know. I mean, this is what I remember. I could be misremembering. If this is true, isn't it sort of really bad news for your QS argument? Because if your QS in natural units is way above TC,
no. Okay, so I see. So this is actually a very important point. So yeah, this is a very important and interesting point. That is a crucial difference between the instanton physics and real-time spiral physics. Okay, the instanton is strongly suppressed at high T. Okay.
Yes.
But the real-time winding, fluctuation, that is enhanced by the temperature effect. Okay, the spiral process. Well, it is very well known that if you see the parametric time, temperature dependence, instanton excitation is suppressed exponentially by exponential minus some by screening mass times the temperature or something like this. But the spiral transition rate is proportional to T to the fourth.
Even though it's a non-perturbative, I mean, it's still sort of a non-perturbative effect, and you have asymptotic freedom at a certain point, right?
Yeah, so the point is that the spiral process is actually can be perturbative. This is a crucial difference. Instanton is always tunneling, and so it requires some topological winding configuration, and that is why it is exponentially suppressed. But the spiral process is real time, and that goes on top of the potential barrier, and so even the perturbative fluctuation can change the winding number. Okay. So that T to the fourth comes from the perturbative zero winding sector actually. Zero winding sector can change the winding number. So that is a crucial difference.
I need to understand it, but okay, fair enough. Fair enough. Okay, thanks. This clarifies things a bit. Further questions? Okay.
Time for Kenji to sleep, right?
Yeah, that's true. Thank you very much. Thank you for taking your time to yes. I'll stop recording. I'll stop recording.
Thank you, Kenji.
Okay, thank you very much for nice discussions.
Yes. They want to stop.